electronegativity and bond polarity. So I noticed over the weekend a couple of you got a little mixed up between electronegativity and electron affinity. They're kind of similar in idea, but they're very different concepts. So we're going to learn about electronegativity. So obviously, representing electrons as dots is a drastic oversimplification. We've learned about quantum mechanics now, right? What are the electrons doing? It's hard to explain, isn't it? The best thing I can say is it's like a standing wave around the nucleus, right? And if you try to look at it and freeze it in space, then you don't know what direction it's moving in. And it's kind of everywhere and nowhere at the same time. So here we are writing electrons as dots on a piece of paper, and we're saying this electron is on that side of the symbol. That's not very realistic. And when we look at sharing of the electrons between, say, a hydrogen and an oxygen, it looks like they're being equally shared. But actually, they are often not equally shared. When they are not equally shared, we have what's called a polar covalent bond. When you hear the word polar, what do you think of? North Pole, South Pole, or polar bears. Where do polar bears live? They live at the North Pole or the South Pole. What makes the North Pole of the Earth different from the South Pole?
We always drive on top.
We always drive on top. It has to do with the magnetic field, right? A compass points north because there's this magnetic field on the Earth, and this north part of the Earth, I mean, it's a sphere. How can it have a point or an end, right? But this one point on the globe, the sphere, has a different magnetic field than the opposite end. That's why a compass works. It'll line up with this magnetic field. So polar, and you think of, well, polar opposites. Well, that's like as different as you can be, right? So in a polar covalent bond, we have sharing of electrons, but it's not equal. And so we get something that's kind of lopsided like this, where the electrons are actually spending more time next to this atom than they are to that atom. And we can indicate this, there's two different notations. One is with an arrow. The arrow points to the atom that has more attraction for the electrons, and then we put a plus at the other end. Or we can use a lowercase Greek delta, delta plus and delta minus. And those represent a partial charge. This is not an ionic compound where we have H plus and F minus. The electrons are shared, but they're not shared equally. So my analogy for this is that hydrogen is one house, and fluorine is the neighbor's house, and the electrons involved in this covalent bond are two little boys. And the two little boys are playing together. Over at hydrogen's house, they have an old black and white TV, and they have a VHS player and some old Barney videos. And if you're hungry, Mom will give you a glass of water and some saltine crackers. This house changes every semester a little bit. Over here at Florine's house, they have this huge plasma TV, and they've got Dish Network with all the channel options. And if you're hungry, Mom will order you pizza to be delivered. They actually have a soda fountain in the kitchen. They have a swimming pool in the backyard. They have their own bounce house and a trampoline. This place is kid paradise. So these two little boys, are they going to split their time equally between those two houses? No way. They're going to play at Florine's house. Why? It's more attractive to the little boys. So this notation makes me think of somebody coming along and saying, where are the boys? And they point. They're at that house. Because almost all the time, they probably are. Do they ever come over and visit hydrogen's house? Sure, they come over. The hydrogen boy probably needs to get a change of underwear occasionally and let his mom know he's okay. But most of the time, they're spending over here. So fluorine is more attractive to electrons than hydrogen is. So in this shared bond, the electrons spend more time around the fluorine atom than they do around the hydrogen atom. And because there's more electron density around the fluorine atom, it has a slight negative charge. And we can see that when we put hydrogen fluoride in an electric field. So here the molecules are just floating around being themselves, and they're just oriented randomly. We apply an electric field with a positive charge on this plate, a negative charge on that plate. They're going to line up. The negative end is going to be attracted to the positive plate. The positive end is attracted to the negative plate. That demonstrates that there's a polarity in this molecule. It's a polar bond. Any questions? Anybody want directions to Fluorine's house?
That stuff is strong, even if it's dangerous.
Well, hydrogen fluoride is that's really strong stuff. In aqueous solution, it's an acid, and it'll eat almost anything. Yeah. So what is electronegativity? This is the definition. The ability of an atom to attract electrons to itself in a chemical bond. Electron affinity is the energy change when an atom becomes an ion by gaining one electron. So they're not exactly the same thing. Electronegativity is inversely related to atomic size. Fluorine is the most electronegative element, and because the noble gases are so unreactive, some of them don't even form compounds that we're aware of, we just leave them out of the measurements of electronegativity. So we just leave them out completely. So here's an illustration of this trend. So remember that as we go across a period, are the atoms getting smaller or larger? Smaller. And the smaller atoms have higher electronegativity. And as we go down, the atoms are getting larger and the electronegativity decreases. So that's one way to keep track of this. It's the opposite trend to atomic size. The way I think of it, though, is fluorine. Fluorine is the best place, the most electronegative. And so if you're comparing two elements like boron and carbon, well, which one's closer to fluorine? That's going to be more electronegative. So in general, the trend goes in this direction, up. So this is the peak. And group 8A isn't on here because they don't even form compounds, really. Now, notice that some of these have the same, like chlorine and nitrogen are both electronegativity of 3.0. This electronegativity scale, somebody just came up with it. You can only measure relative electronegativity, and so he just had to assign something. He says, well, we're going to say that the highest is 4 and the lowest is 0, and then we'll just rank them all in between. So bond polarity. Of course, there's a continuum here. It's not you're polar or you're nonpolar. There's this in between where you're like, oh, you're kind of, where do we draw a line? The degree of bond polarity is going to depend on the difference in the electronegativity. So we often abbreviate electronegativity as capital EN because it's a really long word and we get tired of writing it. Delta EN means the difference in electronegativity. So the arbitrary divisions are that if the difference is from 0 to 0.4, we call that a nonpolar bond. Sometimes it's called a pure covalent bond. I prefer to say nonpolar. If you have an electronegativity difference between 0.4 and 2.0, that's still being shared, but it's called a polar covalent bond. If the difference gets above 2, then we consider it to be an ionic bond, and the ions are transferred. But these divisions are arbitrary. Yes?
So what's the difference actually like 0.4? Is like a nonpolar or polar?
That's a good question. What if it's right on the line? Well, let's find an example. Let's find two things that would be different by 0.4. Phosphorus and carbon. There's a good example. So phosphorus and carbon, 2.1 and 2.5. We'd probably say that that was nonpolar. And some of these, like if you have a bond between nitrogen and chlorine, that's definitely going to be nonpolar because they're the same. Hydrogen, being his own weird little self over here, sticking way up. Hydrogen with carbon is a difference of 0.4, and that's generally considered to be nonpolar.
Is that just because they're both nonmetals?
It's not just because they're both nonmetals, because if we look at, say, nitrogen and oxygen, the difference is 0.5, and that would be polar. What I want you to be able to do, if you're given the table, then you can compare electronegativity values. But that's really not necessary most of the time. So well, let's see if I have it written down. I don't. What I would say you should know in general is if you have a covalent bond, and you can identify covalent bonds because it's two nonmetals. If you have a metal and a nonmetal, say that's ionic. If it's two nonmetals and they're the same atom, like hydrogen and hydrogen, obviously that's going to be nonpolar. If they're different, most of the time it's going to be polar. Not always, but most of the time. So that's kind of just the general being able to predict. But there are some between different elements like carbon and sulfur. They're different elements, but they do have the same electronegativity. But I would not ask you to predict that that's a nonpolar bond without giving you the values. In no way should you memorize those. That's dumb. A dipole moment is another way to measure the bond polarity. It's abbreviated mu, and the dipole moment occurs anytime we have a separation of positive and negative charge. So dipole moment is Q, the charge magnitude, times R, where R is the distance. Because the dipole moment is going to be different if you have large atoms or small atoms. A common unit for this is the debye, which is capital D. We're not going to use this very much, but a debye is 3.34 times 10 to the minus 29 coulomb meters. But looking here, chlorine, we look at that, two chlorine atoms, and we can predict, well, that's going to be nonpolar. The electronegativity difference is 0. The dipole moment is 0. Chlorine fluoride, electronegativity difference is 1. If we calculate the dipole moment, it's 0.88. Hydrogen fluoride, lithium fluoride. Lithium fluoride, is that a covalent compound? No, that should be ionic because it's a metal and a nonmetal. Look at the electronegativity difference, 3.0. That's definitely going to be an ionic compound. Here, the hydrogen fluoride, 1.9, that's just under that 2 difference. And we would predict covalent compound because it's two nonmetals. And in the dipole moment, we see this jump from 1.82 up to 6. That's a big dipole moment. Another way to think about the polarity is percent ionic character. So this takes the ratio of the bond's actual dipole moment to the dipole moment it would have if the electron was completely transferred. So comparing what it actually is to what it would be if it was transferred. It's important to realize that no bond is 100% ionic. It's more convenient for us to think in absolutes. This electron was completely transferred from sodium to chlorine. But in actuality, there's a little bit of sharing even in ionic bonds. So if we have over 50% ionic character, then we consider the bond to be ionic. So if you graph this, percent ionic character versus electronegativity difference, we see these clusters. And look at the elements here. These are all nonmetals, right? And they all fall below this 50%. In fact, they're below 25% ionic character. Up here in this cluster, what are most of these? They're metal-nonmetal compounds, right? So we would predict that they're ionic. And then hydrogen fluoride is in there too. But look, he's under the 50%. So this method says, well, if it's over 50% ionic, then we'll call it ionic. So it's another way to do groupings. But all you really need to remember is metal, nonmetal, ionic. Non-metal, nonmetal, covalent. So we should be able to classify bonds. Determine whether the bond formed between each pair of atoms is pure covalent, polar covalent, or ionic. And I'm going to call that nonpolar. So between iodine and iodine, pure covalent or nonpolar. So this is a nonpolar covalent bond. Because here, those two little boys playing together, both of the houses are the same. So they're going to divide their time equally. There's no reason for them not to. Cesium and bromine. Ionic. How do you know that? Metal, nonmetal. Cesium's a metal, bromine's a nonmetal. So this is ionic. Ionic is really just extreme polar. This is where maybe instead of hydrogen and fluorine, we had sodium and fluorine. And sodium, that house is just so atrocious that the fluorine house actually adopted the kid, right? He's not even part of the sodium family anymore. He moved in next door, transferred. How about phosphorus and oxygen? We would predict that that is polar covalent. Now let's go check and see if we're right on that. So here's phosphorus, and there's oxygen. And yeah, the difference there is more than 0.4. Any questions?